In this paper, we present a system to automatically generate a suitable rigging for a multi-component character. Imagine that the user wants to animate the shown multi-component character. Such 3D models are available, for example, from large 3D model repositories on the internet. These 3D models are typically not rigged with an animation skeleton, and the individual components are not labeled. Generating such a rigging is a difficult manual process, which can be automated with the system presented here. The users of the system can select an animation skeleton that defines the motion that they want to apply to their 3D model. The system then automatically generates a joint mapping between the generated skeleton of the multi-component mesh and the input animation skeleton. This joint mapping can be used to animate the multi-component character with the desired motion. Given a multi-component mesh, the first step in the processing pipeline is the segmentation into components. Based on this segmentation, an analysis is performed to determine which components are in contact. Here we show the generated contact graph. This contact graph is typically quite complex and is not directly suited for rigging of the input model. The contact graph is then simplified to a tree by clustering nodes. Here we see how the clustering algorithm iteratively generates a coarser representation of the contact graph. Finally, only a simple tree structure remains. During joint mapping, we find the optimal mapping between nodes in the high-resolution clustering and the joints of the animation skeleton. This allows transferring the motion of the animation skeleton to the input model. In the following, we show some results for different input models. This is a relatively simple example where the contact graph is not too complicated. As the model has the same number of limbs as the selected animation skeleton, we get a one-to-one mapping of the limbs. In this example, the contact graph is already quite complicated. Nevertheless, the graph clustering generates a plausible target skeleton. This model has wings that are interpreted as additional arms by the system when they are mapped to a human animation skeleton. This lamp example has a morphology that is quite difficult to match to a human animation skeleton. The system still finds a reasonable solution by mapping the upper part to the torso and the lower part to one of the legs. This is a very different input mesh that was generated by dividing the armadillo model into a large number of separate components. The graph clustering works well and successfully generates a coarse skeleton and rigid skinning for this input. Here is another robot example. Let's see if we can teach this rough-looking robot how to perform a beautiful ballet dance. In this final example, we are running the automatic pipeline on an input mesh that shows some resemblance to the Buzz Lightyear character in Disney's Toy Story. Again, the approach succeeds in finding a good rigging. Thank you very much for your attention.